Okay, so let's come back to our lecture, chapter 3. Again, this is our third lecture on this chapter, and we've been talking about vectors as our first part of the lecture. Mostly is how to add two vectors together, two-dimensional vector together. Okay, and we cannot just add them like numbers. Okay, this is this is the first thing you need to know. And then we develop a specific rule of adding two vectors geometrically by connecting them like this, or algebraically by using the component method to get the number. Okay, get the number. Basically, we find the components first, and then we add the x component together and y component together to obtain two components of the sum. And then that might be the final answer, or we may go back to find the length and angle of the sum. Okay, so, and we did some examples here. Okay, as I said, there's basically roughly three parts of this task. First of all is how do we find the components given the length and angle. Secondly is how do we add the components. And thirdly is how do we figure out the length and angle given the two components. Okay, so out of the three parts, for this chapter, you need to definitely understand everything, but for later chapters, the first step here is the most important one. Given the length and angle, you need to be able to figure out the components, okay, using trigonometry. Okay, so this is where the trigonometry is used in this class. It's probably the only case that the trigonometry is used in this class, okay, by for finding the component of vectors. Okay, and then we talk about the part 2, 2D motions. We applying the idea about vectors we learned here. So roughly speaking, we still use the same quantities to describe 2D motions, and they're just becoming 2D vectors now. Though they can point any directions in this two-dimensional plane. It sounds very complicated, but the idea is, we use a component method. We can break down to the x component and y component, and they basically behave like a 1D motion for each component. So a 2D motion is basically equivalent to two 1D motions, okay? And then we start to use this idea for the projectile motion. As I said, the projectile motion is such that the vertical direction is like a constant acceleration motion, like a free fall, while the horizontal direction here is like a constant velocity motion, okay? So that's the key for studying projectile motion, okay? So the x component is constant velocity, y component is constant acceleration. And we kind of did it qualitatively, and then we went ahead and did this example, and we haven't really finished it, so let's do this right now. Okay, let's continue right now for this example. Okay, I got a message again. Oh, that's fine. Okay, so let's talk about this. So again, this example is a long jumper, right? Remember we have a long jumper here, so let's hopefully we do have this. Yes. So this is the problem we have, the long jump, okay? So the long jump jumps from here all the way here. Essentially, it's a projectile motion. This person basically threw herself into the air, you know, like that, okay? And then we're given the initial velocity, both the magnitude and the angle. We're asking a bunch of questions here. So we're looking for the time to reach the maximum height and the maximum height, and then how far it goes horizontally, okay? So as I said, for any two-dimensional problem we do here, the only way we know how to do it is to break it down to two one-dimensional problems. So you're given something like this, like VI and angle, it's not useful. You cannot use them directly, those numbers. You have to find the components of these quantities first before you go further, okay? Otherwise, because they're not either along X or Y direction, you cannot use them. So break them down to their components like this, okay? And then let's look at the first question here. The first question we're asking time to reach the maximum height, because the maximum height is the idea of vertical direction. So it's natural to look at the vertical direction, and then you can draw this diagram again, and then write down what do you know about the vertical direction. We have initial velocity, final velocity, and acceleration. Notice these two pieces of information, they're not given explicitly in the problem, but you need to realize they're there because it's a constant acceleration motion along the y direction. Okay, so we got 3 pieces of information. We're looking for the time and displacement. So again, remember, this goes back to our previous chapter. Given these, let me pull out the, there's a bunch of stuff on my screen, so it's kind of hard. Draw, okay, this one, okay. So remember, we have this 4 formula we can use, right? First one is about velocity. Okay. Let me erase it. I need to fix my eraser, but okay, this works for now. So remember the formula we had before were like this: VF equal to VI plus A times delta T, and then delta X equals to VI plus VF divided by 2 times delta T, and then delta X equal to VI delta T plus 1/2 A delta T squared, and then finally delta X equal to excuse me, VF squared minus VI squared divided by 2A. Okay, so we got these 4 formulas to use, right? Now they're good for 1D motion, but they're good for this Y component as well. Okay, and so one thing you should notice here is normally when I give you those formulas, I give them in a general format, meaning that I have VF, VI, and A here specified, right? I mean, I didn't call them VI, Y, AY, VFY. It is up to you to realize that you could use those formulas for the Y direction, and you should plug them the corresponding Y component to those formulas instead of using this VI directly, because this is nonsense, right? Because this goes like towards the arbitrary direction. It's not a one-dimensional motion, so you cannot use those formulas there. So so that's why I'm saying you need to understand the physical meaning behind the formulas to use them correctly, you know, like what we're doing right now. So out of these 4 formulas, right, we're looking for delta T. Which formula do you think we should use to get delta T? Which one's the best for this solution? Again, send me a message. Just send me a message. Just tell me what first, second, third, fourth, you know. Okay. I got answers, some answers. Well, there's all kinds of answers. Somebody says fourth, first, second. Okay. Again, how do you tell, right? You need to, again, the formula you need is something connect the given information to something you unknown, so to the unknown, right? So let's start from the first one here, okay? Out of these formula, we're given VF, VI, and A, and we're looking for T. So this is perfect for us, okay? Well, what about second? Okay, it's not good for delta T because we have 2 unknowns here, so we cannot solve for them. And third one, same thing, 2 unknowns, okay? Last one, yeah, we can use the last one, but not for delta T, but for the displacement, okay? We can use that for that, okay? So let's do them. Let's use this one for delta T and this one for delta Y, okay? So again, I give you the formula in one form, but you can certainly manipulate it. So you have a VF. Well, let's do the first one, okay? So we're looking for delta T, right? So VF equals to VI plus A delta T, okay? And we need to find delta T, right? Some of you want to plug in numbers right away. I don't blame you. You can do that, but I normally manipulate a little bit first. So I got delta T equals to VF minus VI divided by A, okay? So I can just plug in numbers here. Now, actually, we have, let's use our problems symbol. So we have VYs. We're looking at the Y component, right? So this is all Ys, okay? Now, if we plug in numbers here, we got VY 0, VY final 0, VY initial is 3.76. So 0 minus 3.76 meter per second divided by acceleration is negative 9.8 meter per second square. As you can tell, right, this is totally our last chapter problem, okay? So at this point, you use your calculator, 3.76 divided by 9.8, and you got 0.38. Okay. So this is the time it takes to reach the highest point. Okay, reach the maximum height. Okay. Now let's do the delta y here. Okay. Again, as I said, this the last one here is the best to do. Notice that this formula gives us delta x because when we're talking about 1D motion, we only had x direction, but now you're doing delta y, right? So, but it's the same formula. You just need to, that's 8. I'm sorry, I didn't write it well, 8. So you write it like in our case, delta y equals to Vy final square minus Vy initial square, okay, divided by 2ay, right? Now, if you plug in numbers here, again, we have 0 and then negative, minus 3.76 meter per second, the whole thing squared, and divided by 2 times negative 9.8 meter per second squared. Okay. Okay, so, and then this is basically, you take this divided by that, right? So you get 3.76 times 3.76 divided by 19.6. Okay, so you got 0.72 meter. Okay, so the highest, the maximum height for this jumper to reach is 0.72 meter. Again, as you can see here, what we're doing here is nothing different from what we did in the previous chapter. It's just the basically same thing, right? And okay, we're done with part A and part B. Let's do part C. Part C asks you how far it goes, which is basically displacement along the x direction, right? Well, along the x direction, as we know, it is a constant velocity motion. Constant v motion in x direction, okay? So for that motion, we only have one formula, basically x equals to v delta t. It's a constant velocity. So if you know the time, you multiply by velocity, you got your delta x, okay? So, okay. So in this problem, we're looking for delta x, right? So do we know v? What is our v? What value should we put in for v? For this, to use this formula here. If you want, you can send me a message, okay? Okay, I got a message. Let's see. Let's see. 10.3. Okay, that's correct. Yes. So basically, we shouldn't use 11. Remember, right? Because 11 is not along the x direction. So what we should use is the x component of the velocity, which we calculate here as 10.3. Okay. So we should use 10.3. That's good. Actually, it's better if you write x here to remind you that this is the x component. And what about delta t? Do we know delta t here in the problem? 0.83, no. Okay, remember this 0.83 is the time it takes to go from the starting point to the maximum height. Okay, so it's like going to here. It's like halfway of this motion. So strictly speaking, we do not know delta t, but you could guess delta t should be doubled of what we had before. Remember, we did one problem for free fall motion. It's like if something goes up and then comes back, it takes double amount of time for it to start from here, goes all the way back. Compared with start from here, go to the maximum height. Okay, so this is like some if you want to like a shortcut. Okay, you can use that shortcut to do cut. So basically Vx equals to as we explained 10.3 meter per second, and then delta t equals to 0.38 second. Oh, sorry, times 2. Okay, so that's 0.76 second. Okay, so so we have these two, and then we can just plug them in. Now, if you want, you can double check this delta t, right? You can calculate it using. You can actually go ahead and calculate the time it takes to go from here all the way back here. It's just one dimensional, by using the y direction. So in that case, you would use the second formula, the third formula here, by taking delta y equal delta y equals 0. So you can let me calculate that. You don't have to do that when you do your homework or the test, but I just want to show you guys it is the true. So now remember I'm looking for a different motion right now. I'm looking at the motion like this, the whole motion like this. So this is 0 here. Okay, this is 0. Okay. Well, if this is 0, you can factorize delta t. You have delta t and then vi y plus 1/2 ay delta t. Okay. So for this equation to be satisfied, either delta t is 0 or this whole thing is 0. So we're looking for this part here. So we have vi y plus 1/2 ay delta t. Okay, sorry, this is plus equals 0, and then we can solve for delta t. So delta t is 2 vi y divided by ay with minus sign. So that's like 2 times negative 3.76 meter per second divided by negative 9.8 meter per second squared. Well, as you can see, right, just by comparing this and this, you see this is just exactly 2 times of the time. So it is indeed this 0.76 second. Okay. Now after that, you can plug them back in to calculate delta x. Okay. So delta x equals to the velocity component, which is a 10.3 meter per second, and times the time 0.76. So from there you can figure out the distance it goes. Okay, 10.3 times 0.76. Okay, so we got 7.8 meter. It's pretty far, but probably not breaking the world record or something, you know. But 7.8 is pretty decent. I don't think I can jump that far, you know. Okay, so any questions about this problem? Okay, again, as you can tell here, right? We're doing essentially one-dimensional problem. But we're doing not one of them, we're doing 2 of them. One for y component, one for x component, depending on what you're looking for. In this case, see, these ones here are related to the y component, this one's here related to the x component, okay? So, and this requires some analysis, okay? If you just look at the problem, it's like whole thing's maxed up, right? So it takes your analysis, okay, by drawing here and then separate the component here and then realize these are related to y, this is related to I, then it becomes our old friend of one-dimensional motion. Okay, if you don't have this analysis part, it's gonna feel hard. Okay, so when you're trying to do a homework problem or solving like a exercise problem in class, try to take a look at what I'm doing here and try to do a similar analysis. Okay, and then after it becomes a one-dimensional problem, you should feel comfortable because that's like our old friend. Okay, sorry, I have some loose connection here. Okay, so that's the important thing. But again, these problems are a little bit harder than the problem we saw before in 2D when we have 1D motion, but it's not too bad. It's not terrible. Okay, and actually, let's try to derive something kind of in general for this motion. One kind of a common question. There are 2 kinds of things we can derive based on what we already did for this example. Okay, one is like let's show this. This shape is a parabola. Okay. Maybe you call it consequence. Parabola. Okay. Now, as I told you guys, for a projectile motion, if we ignore air resistance, is a perfect parabola. Okay. Why? We can actually show that. Okay, by using the formulas we had before. So let's say, so the idea is this, okay? The idea is like we can write delta y in terms of delta x, then we can actually show that it is a parabola, okay? So how do we do that? Okay, well, let's try to, let's see, let me use this formula here, okay? So for the y component, okay, y component. You have delta y equals to VIY delta t plus 1/2 a delta t. Okay, maybe this is, no, this is probably too complicated. So let's do another one. Delta y equals to VIY plus VFY divided by 2 times delta t, right? So, and then let's try to, wait, is that, no. Okay, I guess it's the same, sorry. Because we need to plug in VFY here. So yeah, let's go back to the previous one, sorry. Let me use my eraser. Okay, let me go back to the first one. Okay. Delta y equals to VIY plus delta t plus 1/2 AY delta t squared. So we also know delta x equals to VIX or VX because it does not change times delta t. So the idea is we can express delta y through delta x, then we can see it's a parabola. So let's let's solve for delta t here formally. So if delta t equal to delta x over Vx, and then we'll plug this back in here, then we'll get delta y equals to VIY delta x over Vx plus 1/2 AY delta x squared over Vx squared. Okay, so for a given motion, the acceleration along y direction is constant. VIY and VIX are both constant because this is determined by the initial velocity. And as you can see here, y goes like x squared. So there's an x squared term and then x. So that's definitely a parabola, right? If you still remember your analytical geometry course from either high school or college algebra, then you know this is a quadratic formula, and then this represents a parabola, okay? So this is basically a general expression for parabola, okay? Well, if you don't know it, that's fine. You know, you're not required to derive this kind of thing. So just this will be something you can learn from here. Okay. Now another part another common asked question is how to throw a ball far. Okay. Well, there's a lot of practical needs for this question, right? For example, you are outsider playing baseball, and then you want to throw the ball back to the home base, right? You want to throw it maybe really far, right? Well, you're limited by whatever power strength you have in your from your muscles, right? But the question is, how do we take advantage of the physics we learned here so to throw the ball far? Same thing. You have same problem when you try to throw a football, right? Sometimes you want to throw the football really far, even basketball sometimes, right? So the question, how do we throw the ball far? Well, that question is required. I mean, basically, it's like, again, it's basically coming from here, right? So see, according to this one here, right? Okay, let's start from something fixed, okay? So what you can, what is fixed is the initial velocity here, VI. This VI is basically determined by the strength of your arm, right? You cannot easily change it. You can try to do exercise, but that's not the consideration we have. Suppose you are what you are, right? You want, given what you have, how do you throw the ball far? Now, it seems like the only thing you can change here is the angle, that you can throw the ball, okay? So you can, by changing the angle, you have a feeling that the distance will be different. Now, what do you guys think? If you want to give a guess, which angle you think is the best for throwing the ball? Again, you can send me a message, you know. I guess if you have played some sports, it may help a little bit. Maybe you already have a good intuition about that. Okay, one person said lowest angle possible. Another person said 50 degrees, okay? Okay, let me argue like this, okay? Think about it, right? Say for the same velocity, right? Let's say, suppose you want to throw it really low, like really small angle, okay? Well, it doesn't seem like it's gonna work well because if you throw it really low, I mean, the ball is gonna go up a little bit and then go back to the ground pretty quickly, right? Now, you know, in this extreme case, you throw horizontally, it's gonna just fall right. I mean, so low angle, low theta is not good, okay? Not good, okay? Now, if you go to another extreme, like say, let's try some really high, so let's say really like this, really high. Well, in this case, it takes a lot of time for the ball to stay in the air because it's the vertical direction, right? It goes really high. However, it kind of wasted, you know, it's like, you're gonna actually, I mean, you can kind of imagine it's gonna fall back pretty quickly, you know, and you can try it easily at home, you know, through a baseball or something for both two cases. It doesn't seem like good either way. So we would think that this is something somewhere in the middle, you know, and it turns out it is exactly in the middle. So how do we do this? So we will write let's start from the displacement on the x direction, right? So this is our Vx times delta t. Okay, now what is Vx? Vx based on this, what is given here, Vx just Vx equals to Vi times cosine theta. This is the x component. So let's plug this Vi cosine theta here. So as you can see, right, the angle theta enters here, but there's another thing that hasn't been decided yet. This is the time, delta t. Well, that certainly is also dependent on the angle because the higher you throw it, the bigger the y component, the longer it's gonna stay in the air. So, and for that angle, we already have something that's like here. So see, okay, see this, we cover here. So see this here, right? See this delta t is given by, for the whole height, right? It's given by delta t equals to 2 VIY divided by negative AY. Well, VIY is just okay, VIY is just VI times sine theta. So you're plugging back here, you have 2 VI sine theta, okay? But AY is basically constant, right? It's just fixed. So as you see here, this delta t depends on theta as well. So if you plug in delta t back in there, you have delta x equals to, okay, you have VI, another VI, so you have 2 VI squared, and then you have cosine theta times sine theta divided by 2 negative AY, okay? So again, this part here is totally fixed, okay? Well, the only thing that's changing with theta is this part, okay? Now, it turns out there is a trig identity, which you don't know. I happen to know this, is 2 cosine theta sine theta equal to sine 2 theta, okay? So if you use this trig identity, it can help you to simplify the formula to this, okay? VI squared divided by negative AY times sine 2 theta, okay? Now you can plot this function, sine 2 theta. So when theta equals 0, sine 2 theta is 0. When theta equals to 90 degree, sine 2 theta becomes sine 180 is again 0. So sine 2 theta goes like this, okay? Well, the highest point is achieved at when theta equal to 45 degree. So when theta equal to 45 degree, sine 2 theta is becomes sine, it's become 90. So you have sine 90. It has the maximum value of any values of a trig function, which is 1. So when theta equals to 45 degree, okay, sine 2 theta reaches maximum, okay, value, okay, which is 1, okay. So correspondingly, delta x reaches maximum value, which is this, okay, VI squared over negative AY, okay. So basically that tells you if you throw ball at 45 degree angle, it's going to be you can throw it the furthest, okay. Well, this kind of makes sense, right, based on what we're talking about here, okay. So going back to our long jumper problem, this jumper leaves the ground at 20 degrees. So it's probably not a good idea. She should go a little higher, jump a little. Well, I don't know. I mean, they can definitely try, practice and adjust the angle. Well, when you throw the ball next time, you try to aim at 45 degrees. I know it's kind of hard, we don't have a protractor to measure our throwing angle here, right? But it kind of, at least intuitively, it's just somewhere in the middle, And maybe you'll surprise your friends or family. Now you can throw the ball really far because physics. You learn projectile motion from general physics 1, and it's going to improve your game or something, hopefully. Okay, did that make sense to you guys? Any questions? Okay, now we got about half an hour. Okay, which is good. So we're done with this discussion of projectile motion, and so it's roughly we're done with the second part. Now there's a little bit left for this chapter, which is about relative velocity stuff, which I'm going to talk maybe a tiny bit. Okay, but before we do that, let's do an exercise together. So we've been doing exercise in the last couple of days every day, which I think is good because you guys get practice and also get some bonus points. So we're gonna do a exercise, okay? We're gonna do about a projectile motion, okay? So the problem here is now I'm not gonna write the whole problem here. I'm gonna just briefly describe it. So there's a bomber here, okay? So we're going back to World War II, okay? World War II, there's a bomber, maybe a B-52. Maybe they didn't have B-52 at that time. B-15 or something. Okay. Anyway, the bomber want to go and bomb a, let's say, military base. Okay, a building, military base building. Okay. Let's say the height of the bomber flying is 100 meters. Okay. Okay. The first question I want to ask you guys, okay, we want to bomb the building. Where should we drop our bomb? Okay, should we drop the bomb when the bomber flies on top of the building, or should we drop it before? Okay, now based on what we learned from this chapter, we shouldn't drop it right here because if we drop it right here, the bomb will have the same initial velocity as the bomber, which is horizontal. So if we drop it from here, it's gonna go like projectile motion, it's gonna hit here. So if you wanna miss, you should drop right on top of the building. If you drop right on top of the building, you definitely miss your target. So that tells us we have to drop the bomb before the building, right? The question is where should we drop it, okay? So let's say this height is 100 meters and then the velocity, initial velocity is horizontal. And let's put it like I don't know, 200 meters per second. Okay, this might be a little bit too fast for the bomber, but let's just use it as number. Okay, now I know some bombers they do like this. They do it like this, drop the bomb and then go up. But for simplicity, let's just say that this bomber is gonna go with constant velocity. Like 200 meters per second. Okay, and maybe let's change it 150. Okay. 200 is maybe too big. Okay, let's use 150. Okay, so 150 meters per second. Okay, horizontally. Okay, now there's two questions I want to ask. Okay, question one: how long does it take for the bomb to reach the ground? Okay, time for the bomb to reach ground. Okay. And two, so how far the bomb should be dropped to hit the building, okay? How far away the bomb should be dropped to hit the target. Okay, so these are the two questions I'm asking here. Okay. Again, okay, this problem is a projectile motion problem, but it's a little bit different from the previous problem. The former, you shouldn't use the former directly from the previous one, but what I recommend you guys to do is to use the same way to analyze the problem. You know, draw the picture, separate the motion into two components, and then look at the appropriate component to solve the unknown. Okay. So let's talk about this together. Again, as I keep saying that there's nothing wrong to get the wrong answer, you know, because we're learning something, you know. So for this problem, the first part asks you how much time it takes for the bomb to reach ground. Well, again, the time is mostly determined always by the vertical direction, because horizontal direction is just going forever. So whenever you ask about time, you should probably go to look at the vertical direction. So for this part, we'll use the vertical direction, and for this part here, we'll use the horizontal because it's asking about how far, right? So let's look at the vertical direction. What do we know about vertical direction? Okay, so in this case, I'm not actually going to set up the coordinates like this because it's a little bit more convenient. So if I do like this, my initial velocity vi, there's only x component, so that's 150 meter per second. Okay, so my initial velocity on y direction is 0 because there's nothing in there. And then the acceleration along y direction is going to be positive 9.8 meter per second squared because I choose the positive direction going down. And I also know the displacement along the y direction is going to be 100 meter, right? So based on these three conditions, I can solve for delta t. The best formula to use is this formula here. So in this case, VIY is 0, so this term is totally gone. So the delta t can be solved by using this. So you have delta t equals to 2 delta y over ay, and then square root, okay? So you have a square root of 2 times 100 meter divided by 9.8 meter per second squared, okay? Now you got 4.52 meter a second. So if you were like me, you forgot to take square root, you got 20.4 seconds, but that's wrong. You have to take the square root, okay, to get 4.52, okay? So I made a mistake by not doing that, okay? Yeah, you've got 4.5. Again, the unit should be second because you're doing time, you're calculating time. You're not calculating the velocity, okay? Now, after you got this first part, the second part asks you how far it should be dropped before, to hit the target. So that means we require, so with the given velocity, right, the displacement delta x, so the bomb is gonna move along the x direction by this much, okay? And the time is determined by the vertical direction, and then the velocity given is the same velocity as the velocity when right after it's dropped, right? Because going horizontally is the constant velocity motion. So you have 150 meter per second times 4.52 second. So you got something like 678 meter, 78 meter, okay. Okay, yeah, that's correct. So you can run, if you run a little bit, it's good. So in the test, so if you run a little bit, that's fine, but make sure you write all the steps, especially you write the equation you use and then plug numbers for the equation and get the answer. That way I know where the number come from. So even if you run a little bit too much, as far as your steps are correct and you didn't, it's not too way off, you still got the full credit. So running a little bit wouldn't matter much, okay? Does that make sense, you guys? Yeah, I'm sorry, my bad that I didn't take the square root for this when I calculated. I don't know what I'm thinking. So, but again, this is a good problem. You know, it kind of help you to see how do we, again, the key here is to consider 2 one-dimensional motions instead of 1 two-dimensional motion, because we cannot do much about the two-dimensional motion itself. And this one's a little bit easier. The important thing to notice is this VI here is going along the X direction, and then along the Y direction, there's no initial velocity. So this is kind of like a hidden piece of information. And if you just use 150 for this direction, you'll be wrong, right? So that's important. Okay. Okay, we're actually we have 4 minutes left. Now, as I mentioned, I thought we want in the last part of this chapter, it talks about relative motion, but I realized that we after we cut off the credit, we don't talk about that anymore. So we're actually done for this chapter. Okay, so starting from tomorrow, we're gonna do chapter 4, basically dynamics. We're gonna talk about Newton's law. Which chapter 4 is probably the most important chapter of this whole whole class. Now, for